Hello and welcome to lesson 11 on derivatives and now the first principle. So today we are going to be practicing applying the definition of a derivative to find the derivative function for any specific function that you're given and use the derivative function to find the derivative at a specific point. So from last class or our last lesson, we remember that the derivative of a function f at any given value of a is f prime of a, and this is equal to this limit. So limit as h approaches 0 of f of a plus h minus f of a. And remembering our function notation, this can also be d of, given our function is actually f of x, this is dy by dx, and it's equal to the same thing. And this has to be provided that the limit exists. So if the limit does not exist, we say that the function is not differentiable at x is equal to a. So our first example today, we're asked to find the derivative of the function x squared, so our quadratic function, and x is -5. So we're going to use this limit definition. So f prime of -5 is the limit of h approaches 0. So first we have f of -5 plus a. This is just f of a plus h, where now a is equal to -5. And we have that f of -5. And we're finding the difference of these two. So we're finding the difference of the output, and we're seeing how much the output changes as h is approaching to 0. As that input value is changing very slightly, how is what's the instantaneous rate of change at a is equal to -5? Now, because it's the quadratic function, we're just substituting. So f of x is x squared. So we end up with -5 plus h squared minus -5 squared. And we're just expanding here. So we get 25 minus 10h plus h squared. And just a reminder, this is a plus b squared is a squared plus 2ab plus b squared. Now, simplifying here, we have 25 minus 25, so we're just left with -10h plus h squared, where we factor out the h to get h minus 10. And that's exactly what we wanted, because if you look at the limit when we first started, the reason why we weren't able to solve this, or even from here, is because of this h in the denominator, because it gives us an indeterminate form of a denominator of 0, so we don't want that value. We can't work with that value. But now I'm able to simplify these two h's to have h minus 10. And now I can actually solve by substitution. So f prime of -5 is now the limit as h approaches 0 of h minus 10, which through substitution is just -10. And in other words, we are saying that m is equal to -10, which is the slope of the tangent to the curve f of x is equal to x squared at x equals -5 is -10. And again, if I asked you to find the equation of the tangent at this point, you would be able to use the point -5, 25. You have the slope, you have the point, so you'll be able to give me an equation of the form y equals -10x plus b. So you would just have to solve for b here, given that y and x. Now, another definition here, which is our first principle. And this is exactly that same limit definition there, just written differently. So this is still equal to our derivative at a point x is equal to a. And here we just write this as x approaching a. And in our numerator, we have f of x minus f of a and x minus a in our denominator. So again, as our input values are getting closer and closer to a, so that difference is becoming 0 as x is approaching a, then how much is the output changing? So how much or what is our instantaneous rate of change? And the way we get that instantaneous rate is by approximating values closer and closer to a by letting x reach a. So these two limits are the same. You'll see me mostly use this one up here, but if the first principle makes more sense to you, please feel free to use that. I've also included an additional video for you on Google Classroom going over the first principle. So um, if you just want to be more like if you want to use this one or build your foundation of the definition of the derivative using limits, please make sure to watch it and make connections to this limit. But again, they're both the same. They both equal to f prime of a. So now let's try the example above using the first principle notation. So here we have f prime of -5, and we write this as now the limit of x approaching -5 of x squared. So this is just the f of x minus, and this is f of -5. Okay, so -5 squared. And in our numerator, or sorry, in our denominator, we just have x minus a, which a being -5, we end up with x plus 5. And in our numerator, we have x squared minus 25, which is a difference of squares. So remember, difference of squares, when you have a squared minus b squared, this is a plus b times a minus b. And that's exactly what I've done here. And same thing as above. The reason why I can't solve this right away is because -5 here, or you'll see it a little better maybe here, -5 plus 5 is 0. And I don't want a denominator of 0. I can't solve that. So that's why I needed to come up with this expression, because now I can simplify these two, and I'm left with x minus 5, which I can actually solve through substitution of x approaching -5. And that's what I've done exactly here. So I just rewrote it as f of prime -5. We get that this limit, which through substitution is -10, which is exactly equal to this -10 here. And I'll add in another piece. If you remember from our lesson, our last lesson, we found that for the function f of x is x squared, we found that the slope of the tangent is actually equal to 2x. And if you remember, this is also the same as f prime of x, or dy by dx, or d of f of x by d of x. These are all the same thing. And now, if I asked you f prime of -5, you would have been able to do 2 -5 to get -10. And that's what we're going to do now in our next example. So considering our quadratic function, f of x is x squared, we want to find the derivative of this function at any arbitrary value of x. So now I don't have a specific point. I want to be able to, I'm just going to be showing you again how I'm getting that 2x and how we can make generalizations about this. So using that definition of derivatives here, we have the limit as h approaches 0 of f of x plus h minus f of x over h. And I'm just now putting those values as the function, which is x squared, and in this case, x plus h squared. And expanding, we have this expression, and if you factor out that h, we are left with h plus 2x. And we can see that I'm actually able to solve this limit as h approaches 0. I can solve by substitution to get 2x. So now I'll encourage you to pause for a moment here and try to solve this using the first principles definition. So if you tried it, you would have got something like this. And you would see that we can actually really solve this. And one important differentiation between the first principle and our the definition of the derivative is this is going to help you when you are finding the derivative at a specific point. But if you want to find the derivative function for arbitrary values of x, so you want to make generalizations, we have to go back and use this definition here. So now I have that 2x, and part B has asked us to determine the slope of the tangents to the parabola y equals x squared at these given values. So let's try that now. And I'm now going to show you another representation. So we had previously m here, but I'm also now going to write this as m is equal to f prime of -2. And this is still 2 times -2, which is -4. So this can either be the slope of the tangent at point -2, so the point is -2, 4 is equal to -4, or you can say the instantaneous rate of change of the function at point -2, 4 is -4. And for the other two, this will just be the slope is f prime of 0, and this is just 0. And or m equals f prime of 1 is 2 times 1 is 2. And same from last class. If now I asked you to find the equation of the tangent, you already know these points because they're given by x squared. And you have the slopes, so you should be able to find the equation of the tangent at any of these points. Now, what can you conclude from the derivative function of the quadratic? And keep in mind, the derivative function is now f prime of x is equal to 2x. So let's look at our graph here for a second. So the blue curve is our function, f of x is equal to x squared. Now, I've given you 2 points. Here is 1, 1, and we have here -2, 4. And the slope of the derivative at these points is given by, so in this case, m is 2. And in this one, we have m. And we can actually visually see that here. So if you remember, slope is rise over run. Here we have rise 2 and run 1, which is 2. And here we have rise would be -4 and run is 1. So we do see that slope in the tangents here. And what they've just done is find the intercept here and just graph the equation of the tangent. And now interpreting this, we have 2 different interpretations, and they mean the same thing. So we can first say that the instantaneous slope at any point is given by f prime of x is equal to 2x, which means that the instantaneous rate of change is at any point is given by 2 of x. We can also say the function has a linear rate of change because this is a linear equation. So in other words, the slope of the tangent changes at a constant rate because it's a linear rate of change. If you alternatively had, for a different function, let me name it g. Oh, and this is actually now another way you might see this. If you have the function g of x, and if g prime of x is x squared, I want you to think how this would change these 2 interpretations. So first, we would say the instantaneous slope at any point is given by x squared. And we would also say the function has a quadratic rate of change. So the slope of the tangent is changing with respect to x squared, and it's not linear anymore. Now, the derivative function is, like I said, we're just generalizing. Instead of finding the derivative at a specific point, we want to have a function such that if I ask you to find the derivative at any given point, you just have to evaluate the output of that function for the given input. And so the derivative of f of x with respect to x, because our input is x, is given by the function f prime of x. I mean, remember, this is just the same as dy dx, where f prime of x is given by this limit, provided that the limit exists. So the difference being with what we previously saw was it was at point a, f of a, or when x was a, and we all that we did was this was a, and this was a, and this was a. But now, because we're generalizing, instead of the a's, we just put x there. So let's try that now. Our next example, we're asked to find the derivative function of the function f of x given by square root of x. And notice here I have my domain, which is x is greater than or equal to 0. And if you remember this function, just to give you a sketch, has a shape like this. So using the definition of the derivative function, we just write f prime of x, that limit, and now substitute our function there. So x plus h is now square root of x plus h, and f of x is square root of x. And we can see that h approaches 0 is going to give us a 0 denominator, so we need to get rid of that h somehow. And those square roots always tell me to work with a conjugate, so we're going to rationalize using that conjugate. So the conjugate now is that first term, square root of x plus h. Because here was a subtraction, now we have an addition, and square root of x stays the same. So square root of x plus h plus square root of x. And again, keep in mind this is equal to 1 because I'm not changing the expression. I just want to rewrite it in a way that's going to be helpful for me. And in my numerator, this will simplify to just h. And in my denominator, I have that h. And this part, I'm just going to keep as is. We can't simplify it any further. But now the two h's cancel out, and we're left with 1. And this denominator, which if we substitute back into our function, we can actually solve through substitution because x plus h for h is 0 is not going to be 0. And so I'll be left with square root of x plus square root of x, which is just 2 square root of x. Now, one thing here is now I have x greater than 0. And because keep in mind here, if x was 0, you would have 1 over 2 times square root of 0, which is undefined. So even though here we had x is greater than or equal to 0, now here it's x is greater than 0. And my question for you is, why don't we consider x 0 even though the function is defined for f of 0? And that's exactly because of this calculation right here. Because if you try to substitute or have the input 0 for the derivative function, you'll see, and this is just f prime of 0, right? This is not defined. So a key information or a key learning here is that you have to both acknowledge the domain of your original function and the domain now for your derivative function. So they're not always going to be the same because as you can clearly see, the derivative function changes. It's not the same as your original function. So you have to consider it as a separate function with its own domain. Now, our next example, we're asked to find the equation of the tangent to the graph of f of x is 1 over x. And now we have a specific point again at x is equal to 2. So first, consider the point P. Given our function f of x, we have f of 2 is 1 over 2. So our point is 2 and then half. And we want to find f of x at x is equal to 2. But one thing we're going to now start practicing is to find the derivative function, not necessarily f prime at 2. And the reason for that is, consider, for example, you find f prime of 2 using the limit in part A. And part B or C asks you to now find the derivative or the slope of the tangent at another point. And now you have to do that limit work all over again for your new point. But if you have f prime of x, then any x value that they give you, you already have an expression or an equation for the derivative, and you can just use that value to find the slope. So here, f prime of x using that limit definition, and again, when I have rational functions, I always just separate my numerator so it's written a little bit more nicely instead of having like a fraction over a fraction. Now here, this is just 1 x plus h and subtract 1 over x. And this 1 over h is just my h denominator from here, just rewritten to look nicer. So we're going to solve first the numerator, or that first bracket, by finding our common denominator. And again, notice here, I'm just leaving my denominator because you don't need to expand again. Usually in this process, as you can see, we found that, or we find the h that we need to cancel out with. So this part, you don't need to add extra work for yourself and try to expand this. Just leave it as is. So now going back to our limit, or our derivative, this is now the new expression for our numerator, so negative h over x times x plus h. And now that h that was giving our indeterminate case is gone, and we're just left with negative 1. Now, this one, looking at h approaches 0, I can actually solve through substitution, and it's not going to give me an indeterminate case, and I'm left with negative 1 over x squared. And here, keep in mind, it's for x greater than 0. And this is actually in the same as my original function. Here we had x, it should just be x is not 0. And here, same. We have x is not equal to 0. So we could actually have x less than 0 here as well. It wouldn't change whether our derivative function is defined. But at x is 0, our derivative function is not defined. Now, you were asked to find the slope at a given point, x is 2. But now having this equation, so let me just rewrite it here. I can ask you now the slope of the tangent at any x value other than x is 0, and you will be able to use this equation to give me that slope. So now let's try it for x is equal to 2. So f prime at 2 is going to give me negative 1 over 2 squared, which is negative 1 over 4, or negative a quarter. And we knew the point as well, the point 2.5. So substituting, we want to find linear equations such as y equals mx plus b. So I have my slope there, and if I substitute the values of 2.5, I'll get my b is 1. And I can also rewrite this in this format. And if you remember, this is called the standard form for the linear functions or linear equations. And these two both mean the same thing. And now, looking at our graph, so in the blue we have our original function y equals 1 over x, and this is that point we were looking at, 2.5, and this is now the tangent. And we can exactly see it has a slope of it is negative, so it's decreasing. It has a slope of 1 over 4, so the rise would be 1 and 4. And it has that intercept at plus 1. And we can exactly see that is the tangent to the curve at the point 2.5. Another concept is now the normal. So the normal to the graph of a function y equals fx at a point P is the line that is perpendicular to the tangent at point P. So if you remember, perpendicular would be, I'll just show you on here, it would be, for example, something like this, where we have a right angle there. So it is perpendicular to the tangent at that point to half there. So for example, you might be asked to determine the equation of the normal line to the graph of y equals 1 over x at that exact point. So I'm just using the same example so we're not repeating a lot of the work we did. So you already had that m is equal to 1/4. And so the slope of a line that is perpendicular to this is going to be given by 4. And this is back from grade 9, but a perpendicular slope is the negative reciprocal. So the reciprocal is if you like flip the fraction. So instead of 1 over 4, it's 4 over 1, and the negative. So because that one is already negative, now we have a positive. So knowing that now my slope, and this is just the perpendicular side, so the normal slope or the perpendicular slope is 4, and we have our point. Again, you're just solving for b. So in this case example, I showed you the process. So y equals 4x plus b. Given your x and y, we can find that b is equal to negative 5 over 2. And if you look, or sorry, negative 15 over 2. Oh, so this isn't really shown, but it would have been something like perhaps something like that, I think. Because I'm just imagining here, this would be negative 15 over 2. And you can see this has a um, rise over run, which is 4, so it's increasing, and we go 4 up, or 4 up and 1 over, and approximately this is what that normal line would look like. And of course, it is perpendicular to the tangent. And you can always graph this for yourself as well as these two just to see it for yourself a little better on Desmos. But yeah, approximately that's what it should look like. And now let's look at our final example. So consider the cubic function f of x is equal to x cubed. And for now, I'm just telling you the derivative function is f prime of x is 3x squared. But if you're really curious, you can use those the definition of a derivative with limits to try to find this. I might show you at the end as well if you want to check. But pretty much here, f of x is x cubed. And, oh, this is missing. This should be f prime of x is 3x squared. And my question for you is, does the function f of x is x cubed, so our cubic function, have a negative slope? If so, where? So remember, the slope is given by the derivative. So f prime of x, given that this is 3x squared, and using what we know about x squared being greater than or equal to 0 for all values of x, then this is also greater than or equal to 0 for all values of x. So then actually no, the cubic function does not have a negative slope because the function that gives it our slope is greater than or equal to 0 for all values of x. So if we look at this visually, you can see that any point you choose to draw the tangent, it will always be a positive tangent for that cubic function. And to justify your response, this is pretty much what you're telling me, and just answering it with math, like answering it with verbal reasoning, as well as using your mathematical notation there. Okay, and I did want to briefly show you how we get that 3x squared if you were very curious about it. So I'm just using my definition of the limit for the derivative, and now I will just substitute x plus h for the cubic function and just x cubed. And this is just the expansion of the like a binomial that's cubed, so x cubed plus 3x squared h, 3x h squared plus h cubed. So it's just that exponent is decreasing for h and or for x and increasing for h. And so we can see that the x cubes are canceling out, and all my three terms have an h in them. So if I factor out that h, I'm left with 3x squared plus 3xh plus h squared. So simplify these two, and now I can actually substitute h equals 0, and this will be defined, but because these two have h, they will just be 0, so I'm just left with 3x squared. And that is our last example for this lesson. So you have some practice problems there and some additional work posted on Google Classroom. So please check those out. And as always, if you have any questions, don't hesitate to reach out, and I'll see you all next class.